So here is a linear equation system, ax equals b. We are having a coefficient matrix, which is 3 by 3, a variable vector, which is 3 by 1, and we are having a b vector, which is also 3 by 1. So it's a 3 equation system with 3 variables. It's linear, so potentially we could have a solution here. We could either have a unique solution, we could have no solution, or we could have an infinite number of solutions. And it's quite important to understand what are the situations where you have either a unique, a zero solution, or an infinite number of solutions. And the case of a unique solution is sort of fairly straightforward. That is when your rank of your coefficient matrix of A is equal to 3. So if you have a full rank coefficient matrix, then you have a unique solution. That's the only case where you will have a unique solution. We'll think about the other two cases in a moment. So the first thing we want to establish is whether the rank of A is 3. So we're asking, is rank of A equal to 3? And the answer to that question is yes, or perhaps let me say if and only if, so only if, I should say if and only if, so it means it's a necessary and sufficient condition, if A equals B equals C. Actually, I should not use A equals B equals C because we have a B. Let me use G equals P equals Q is equal to 0 in the following equation system. Okay, so these are sort of three new variables. If and only if G equals P equals Q equals 0 in A1 times G plus A2 times P plus A3 times Q equals 0. Now what this is, we need to figure out what are these A1, A2, and A3? Well, these are the three columns of our coefficient matrix. Okay, A1, A2, and A3. And then we have G, P, and Q, which are just additional variables. So basically what is described here is a 3 equation system. And let us write this down. Okay, so that is looking at the first row of that equation system. That is 3 times G plus 1 times P minus 3 times Q is equal to 0. And we look at the second row, that is 2 times G plus 2 times P plus 2 times Q is equal to 0. And then the third row gives us 0 times G plus 1 times P plus 3 times Q is equal to 0. So what we're having here is a new equation system, and it's almost the same as this one up here, just that the B vector is replaced with zeros, only zeros, so that's here, only zeros. So we're having 3 equations, we're having 3 unknowns, G, P, and Q, and if the only solution to this equation system, and meaning the only values for G, P, and Q, which make all of these 3 equations correct, is that all of these 3 values are equal to 0, then the rank of our coefficient matrix is 3. So this is how we determine whether the 3 columns are jointly independent. Because remember, what the rank tells us is the number of independent columns or rows in a matrix. So you can see that G, P, and Q equal to 0 is for sure a solution, because if you set so this solution, if you set G, P, and Q equal to 0 in these 3 equations, then all of them will be trivially equal to 0. So that will be correct. The question is, are there any other solutions? So we basically, let's give these equations numbers. We basically need to now try and solve for G, P, and Q. Now, the first easy step is here from that last one. We see there's a 0g, so we can just get rid of the 0g. Well, I'll take the 1 away. I will make it more obvious. So you can see from here that P is equal to negative 3q. So then we can use this, let's call that asterisk. So we substitute the asterisk, for instance, into equation 1. That means we're basically getting rid of the P and replace it with something in Q. So we are reducing the number of variables in there. So we're having 3G plus 1 times P, but 1P is negative 3Q. So minus 3Q minus 3Q is equal to 0. So here we get 3G minus 6Q is equal to 0. And we could, for instance, solve that for G. And then we get G is equal to, we bring 6Q divided by 2Q. Okay, solving that for G gives us G equals 2Q. And let's do the same for equation 2. So we replace basically the P in equation 2 with negative 3Q from the asterisk equation. So we're getting 2G plus 2P, which is the same as 2 times negative 3Q. So that's negative 6Q plus 2Q is equal to 0. So we get 2G is negative 4Q is equal to 0. And from that we get G is equal to 2Q. So now perhaps you can see what we found here is for both of these equations, we basically reach the same conclusion. So they are the same. Ideally, what we would like to do is that if you have 2 equations in G and Q, you can then solve them. But these we can't really solve because we get the same relationship. So we're having these 3 relationships now, and they cannot be simplified. But perhaps you can see that if you, for instance, set a certain Q, so let's say we are setting, say, Q is equal to 1, then from this it follows that G has to be equal to 2 and P has to be equal to negative 3. And if you substitute these 3 values into the 3 equations, you will find that they are all correct. So we've already answered the equation here. Is the rank of A equals 3, and I realized I didn't complete that sentence, if and only if G equals P equals Q equals 0 is the only, I forgot to add that here, I think I said it, is the only solution. Only solution to that equation system. Okay, but now what you've established here is that, well, we knew G, P, and Q equals 0 is certainly going to be a solution, but here is a second solution. Okay, and you can test that for yourself. If you plug in these values into these 3 equations, you will find that they are all correct. You'll say, oh, how did you come up with that Q equals 1? Well, you could have chosen any Q. Let's say we choose Q equal to negative 2. Then you will find that G is negative 4 because G is 2 times Q, and P, which is negative 3 times Q, turns out to be 6. And you could plug these three values in to these three equations. You would find them to be correct. So the answer to this question is no. And that means that the rank of A is certainly not 3. It is smaller than 3. It's not a full rank matrix. So we now need to figure out, oh, well, if it's smaller than 3, could it be 2, or could it be 1, or could it be 0? Well, a matrix has a rank of 0 only if all the values are 0, all elements of the matrix are 0. So that's not a case you will encounter here. Well, what's the rank tell us? The number of independent columns. So let's just try and figure out whether these columns A1 and A2, so A1 is 3, 2, 0, and A2 is 1, 2, and 1, whether they are linearly independent. Well, if they were linearly dependent, it should be possible to express A1, for instance, as A2 times some sort of some factor. That's called the factor delta. Okay, if they were dependent, you should be able to say that. So is there any value of delta which makes this correct? Well, to make the second element that's equal here, right? These elements are equal. So for that to work, the delta would have to be 1. But if the delta is 1, then 1 times 1 is unequal to 3. And 1 times 1 here is also unequal to 0. So it turns out that this is impossible here. And that means that A1 and A2 are linearly independent. And therefore, we've established that in that matrix A, there are certainly 2 linearly independent columns. In fact, you could have made that same argument with A1 and A3, or A2 and A3 in this case. Okay, it didn't really matter. All we've established is that there are certainly 2 independent columns. That means the rank of A is equal to 2. So that means in our particular case, we already know that this equation system which we started out with will not have a unique solution because the rank of A is not 3. Okay, so we know in our case, this is not the case. The 2 possible solutions that are still possible is either 0 solutions or an infinite number of solutions. Now, what are the 2 cases here that lead us to this? We now need to look at the rank of A, B, and we'll look in a moment what that means, and need to compare that to the rank of A. Okay, and we'll do that for both of these cases. So the rank of A, B compared to the rank of A. So it turns out that if the rank of A, B is larger than the rank of A, then there is no solution or 0 solution. So I should better say no solution. And if the rank of A, B is equal to the rank of A, then there is an infinite number of solutions. So we know the rank of A already. We established that is a 2. Okay, so now we need to establish what's the rank of A, B. Let me go here. Okay, I'll just give it a bit of extra space. So A was 3, 2, 0, 1, 2, 1, negative 3, 2, 3. That was A. And B was 2, 4, 2. 2, 4, 2. Okay, so what A, B is basically we're putting these 2 matrices together into one matrix. Okay, we are now looking at this entire matrix. So this is a 3x4 matrix. Now the maximum rank the maximum possible rank of A comma B is still 3. Okay, the maximum possible rank. So you need to read that together, is 3. So we can have a maximum of 3 linearly independent columns. Now we already established above that between these 3 columns in A, only 2 are jointly independent. And the third wasn't. So what that meant is that we established that A1 and A2 were jointly independent. And if the rank of that matrix is 3, that means that this third column, this one here, is really a linear combination of A1 and A2. So this isn't really linearly independent. So if we want to find out how many linearly independent columns are there, we can now ignore this column. Turns out you could have also ignored A1 or A2 in this particular case, because all the 3 columns, A1, A2, and A3, were jointly linearly were pairwise linearly independent, but just not as a triple. So you take one column away, and now we are having this third column, and now we are having a 3 by 3 matrix again. And we are again asking, if we want to find out what's the rank of A and B, it is 3, so the rank of A comma B is equal to 3 if and only if that's so this third column will still stick with the name B for this column. So that is going to be that if in, and now we put in the new equation system. So A1, A2, and B. So if A1 times, what did I use? G. A1 times G plus A2 times P plus B times Q is equal to 0, if in that new equation system G equals P equals Q equals 0 is the only solution. So let's go through the same process. We write down this equation system. So we get 3 times G plus P plus 2 times Q is equal to 0, 2 times G plus 2 times P plus 4 times Q is equal to 0, and P plus 2 times Q is equal to 0. So we have that. From here, that's the easiest first step. We get P is equal to negative 2 Q. Now it's actually exactly the same. No, it's not the same, of course, because that 2 was a different value. So P is equal to negative 2Q. But we'll go through the same sort of structure. We replace P in equation 1. So we get 3G minus 2Q. So I've replaced that P with negative 2Q plus 2Q is equal to 0. And from here we get actually 3G is equal to 0 because these 2 bits cancel out. So we actually find G is equal to 0 from here. So that's already different to what we had before. Let's see if we do the same for the second equation. So we get 2G, so plus 2 times P, that's negative 4Q. 2 times P is now negative 4Q. Plus 4Q, that is equal to 0. So what we get from here is again 2G is equal to 0, and therefore G is equal to 0. So we already knew that from here. Just want to confirm that G has to be equal to 0. So the only other relationship we are still having here is P equals to negative 2Q. Now, on what occasion can that be the case? So we now need to think about what possibly could we have here? What could be P and Q to make this true? Well, the one value that will make this true, or a value that will make this true, is if P and Q are 0, right? If P and Q are 0, that will be true. So we are back at the trivial solution, G, P, and Q is equal to 0. That is a solution. The question is it the only solution? Well, we know how P and Q are related. P is equal to negative 2Q. What if, say, Q is equal to 1? Well, if Q is equal to 1, then P is equal to negative 2. G is still equal to 0. Right? There's no other choice for G. So is G equals 0, P equals negative 2, and Q equals 1. So here we have P equals that and Q equals that. Is that a solution? This seems to be okay for our equation. So let's try and plug these values into here. Okay, so we have G equals 0, so that's 3 times 0 plus P. P is negative 2, so that's negative 2, plus 2 times Q, Q is 1, so that's plus 2 is equal to 0. So we get 0 minus 2 plus 2 is equal to 0. That's correct. What about the second equation? So we have 2 times 0 plus 2 times P. P is negative 2, so we get 2 times negative 2. Plus 4 times Q plus 4 times 1, or plus 4, is equal to 0. What's that? 2 times 0 is 0. 2 times negative 2 is negative 4 plus 4. That's 0. And then in the last one, we have P, which in our case is negative 2 plus 2Q. So plus 2 is equal to 0. That's also 0. So what we've established here is that indeed, for G, for the combination of G, P, and Q, 0, 0, 0 was a solution, but also 0, negative 2, 1 was a solution. And in fact, you can get many more. Again, all that matters is that this relation is correct. So if Q was negative 2, we would have G equals 0. If Q was negative 2, P would be negative 2 times that, so it would be 4. That is also a solution, and you could find many more solutions. So again, how are we answering this question? Is this the only solution? And the answer is no. So that means that the rank of A comma B is also 2. We already know A1 and A2 are linearly independent, so that third column is not linear jointly. The 3 columns are not jointly linearly independent, so there are not 3 independent columns, but there are certainly 2. So the rank is 2. So let's see where we are back here. So we now established that the rank here is also 2. So that means that the rank is equal. So this case is also out, and the case we are talking about is this one here. That means in our particular situation, this equation system, AX equals B, with this A coefficient matrix and this solution vector B, has an infinite number of solutions.